Nebulae are vast regions of gas and dust spread across interstellar space. They are not small or isolated objects. Many extend for hundreds of light years and contain enough material to form entire generations of stars. These clouds shape the structure of galaxies and define where new solar systems can emerge. The word nebula comes from the Latin term for cloud. For centuries, astronomers used it to describe any faint, fuzzy object in the night sky. Only in the 20th century did telescopes become powerful enough to resolve their true nature. What once appeared as indistinct patches of light turned out to be complex structures made of glowing gas, cold molecular clouds, and dark dust lanes. Most nebulae consist primarily of hydrogen, the most abundant element in the universe. Helium is the second most common component, followed by trace amounts of heavier elements such as oxygen, carbon, nitrogen, neon, and sulfur. These elements were forged in earlier generations of stars and dispersed into space by stellar winds and supernova explosions. Nebulae are not static. They evolve over millions of years under the influence of gravity, radiation, magnetic fields, and shock waves. Their shapes are constantly changing as gas flows through them, collapses into denser regions, or is blown outward by powerful stellar radiation. In many galaxies, nebulae form long chains along spiral arms. These regions mark the sites where star formation is most active. The Milky Way contains thousands of such clouds, although most are hidden from view by dust that blocks visible light. Astronomers classify nebulae into several main types based on their physical properties and origin. Emission nebulae are clouds of ionized gas that emit light of specific wavelengths. The most common source of this glow is hydrogen. When ultraviolet radiation from nearby hot stars strikes hydrogen atoms, it strips away their electrons. As the electrons recombine with the atoms, they emit energy in the form of light. This process produces the characteristic red glow seen in many nebulae. Oxygen and sulfur contribute green and blue emissions, although these colors are often exaggerated in astronomical images to highlight faint structures. The Orion Nebula is one of the most famous emission nebulae. Located about 1,300 light-years from Earth, it is visible to the naked eye as a faint patch below Orion's belt. Through telescopes, it reveals a dense cluster of young stars embedded in a luminous cloud of hydrogen gas. Inside the Orion Nebula, star formation is actively underway. Dense clumps of gas are collapsing under their own gravity. Some have already formed protostars, while others remain cold and dark, awaiting the conditions needed to ignite nuclear fusion. The intense radiation from massive young stars shapes the surrounding cloud. It carves cavities, compresses nearby gas, and creates shock fronts that trigger further collapse. In this way, star formation propagates through the nebula in waves. Reflection nebulae do not emit their own light. Instead, they shine by reflecting the light of nearby stars. These clouds are usually composed of fine dust particles that scatter starlight, producing a soft blue glow. The blue color results from the same physical process that makes Earth's sky appear blue. Shorter wavelengths of light scatter more efficiently than longer ones, giving reflection nebulae their characteristic hue. Reflection nebulae often surround young star clusters. The stars have recently formed from the same cloud and now illuminate the remaining dust. Over time, stellar winds disperse the material, leaving the stars exposed. Dark nebulae are dense clouds of gas and dust that block the light of background stars. They appear as black silhouettes against the bright backdrop of the Milky Way. These regions are cold and massive. Temperatures can drop to just a few tens of degrees above absolute zero. At such low temperatures, hydrogen exists primarily in molecular form, and the gas becomes dense enough for gravity to begin its slow work. Dark nebulae are the earliest stage of star formation. Within them, small pockets of higher density gradually form. Over hundreds of thousands of years, these pockets contract and fragment. When the pressure and temperature at their centers rise high enough, protostars are born. One of the most famous dark nebulae is the Horsehead Nebula in the constellation Orion. Its distinctive shape is created by a dense column of gas that resists erosion from nearby radiation. Behind it lies a bright emission nebula, making its outline clearly visible. Planetary nebulae represent a late stage in the life of sun-like stars. Despite their name, they have nothing to do with planets. The term was coined in the 18th century because their round shapes resembled the disks of planets when viewed through early telescopes. When a star similar in mass to the Sun exhausts the hydrogen fuel in its core, it expands into a red giant. Over time, it sheds its outer layers into space. The exposed core becomes extremely hot and emits intense ultraviolet radiation, causing the surrounding gas to glow. The result is a luminous shell of expanding gas, often displaying intricate patterns of rings, filaments, and bipolar lobes. These structures are shaped by stellar rotation, magnetic fields, and interactions with companion stars. Planetary nebulae are short-lived on cosmic timescales. Within a few tens of thousands of years, the gas disperses into the interstellar medium, and the central star cools into a white dwarf. The Helix Nebula is one of the closest examples, located about 650 light-years away. Its ring-like structure spans several light-years and contains thousands of dense knots of gas, each with the mass of a small planet. When massive stars reach the end of their lives, they explode as supernovae. These explosions release enormous amounts of energy, ejecting stellar material at speeds of thousands of kilometers per second. The expanding debris forms a supernova remnant. As it plows through surrounding space, it sweeps up interstellar gas and dust, creating shock waves that heat and compress the material. Supernova remnants glow in radio, optical, X-ray, and gamma-ray wavelengths. They are major sources of heavy elements such as iron, silicon, and nickel. These elements become part of future generations of stars and planets. The Crab Nebula is the remnant of a supernova observed by Chinese astronomers in the year 1054. At its center lies a rapidly rotating neutron star that emits beams of radiation like a cosmic lighthouse. Over time, supernova remnants merge with the surrounding interstellar medium. Their energy drives turbulence and helps regulate the cycle of star formation throughout the galaxy. Nebulae are not isolated features. They are part of a continuous exchange of matter between stars and space. Gas expelled by dying stars enriches the interstellar medium. That material later becomes the raw fuel for new stellar systems. This cycle has been repeating for more than 13 billion years. Each generation of stars contains a higher proportion of heavy elements than the one before it. Without nebulae, planets like Earth could not exist. In spiral galaxies, star-forming nebulae trace the shape of the spiral arms. These arms are not permanent structures, but regions of higher density that move through the galactic disk like waves. As gas enters these regions, it is compressed and triggered to collapse. In elliptical galaxies, which contain little cold gas, nebulae are rare, and star formation has largely ceased. In contrast, irregular galaxies often show chaotic distributions of nebulae and intense bursts of star formation. Many nebulae are visible with small telescopes and even binoculars. Their appearance depends on their type and distance. Emission nebulae appear as faint glowing patches. Reflection nebulae show subtle blue tones. Dark nebulae are detected by the absence of stars. Professional observatories study nebulae across the entire electromagnetic spectrum. Radio telescopes map cold molecular gas. Infrared observatories reveal dust-enshrouded star-forming regions. Optical telescopes capture ionized gas structures. X-ray satellites trace shock waves and high-energy plasma. Space telescopes, such as Hubble and the James Webb Space Telescope, have revealed nebulae in unprecedented detail. They show turbulent flows, collapsing cores, and disks of material forming around newborn stars. These observations allow astronomers to test models of star formation, stellar evolution, and galactic dynamics. Every planetary system begins inside a nebula. When a star forms, a rotating disk of gas and dust remains around it. Within this disk, dust grains collide and stick together, gradually building up into larger bodies. Over millions of years, these bodies grow into planets, moons, and asteroids. The chemical composition of the disk determines the types of planets that can form. Water, carbon compounds, and other essential ingredients for life originate in interstellar clouds. They are incorporated into comets and asteroids and later delivered to young planets through impacts. The study of nebulae is therefore directly connected to the study of planetary habitability and the origins of life. Nebulae operate on scales that are difficult to grasp. A typical molecular cloud may contain tens of thousands of times the mass of the Sun. Its densest cores are separated by light years, yet they form stars that can influence each other through radiation and stellar winds. Inside these clouds, motions are slow. Gas drifts at a few kilometers per second. Collapse takes hundreds of thousands of years. From the perspective of human history, nebulae appear unchanged. Yet, over cosmic time, they are among the most active regions in the universe. They are where matter organizes itself into stars and planetary systems. Nebulae are found in every galaxy that contains cold gas. In nearby galaxies, such as the Large Magellanic Cloud, individual nebulae can be resolved and studied in detail. The Tarantula Nebula, located about 160,000 light-years away, is the most active star-forming region in the local group of galaxies. It contains some of the most massive stars known, each emitting millions of times more energy than the Sun. In distant galaxies, nebulae appear as glowing knots within spiral arms, or as extended regions of emission in starburst galaxies. By studying nebulae across cosmic distances, astronomers can trace how star formation has changed over billions of years. Nebulae are the visible structure of the interstellar medium. They connect the life cycles of stars across generations. They record the chemical history of galaxies and provide the environments where new worlds are assembled. Their forms are shaped by fundamental physical laws. Gravity gathers matter, radiation redistributes it. Nuclear reactions in stars create new elements and return them to space. In this way, nebulae represent both the past and the future of cosmic evolution. They are not merely clouds of gas. They are the architecture of the universe on its largest scales and the birthplace of everything that shines. Every atom heavier than hydrogen in the human body once passed through a star and then through a nebula. The material of planets, oceans, and living organisms is inseparable from these vast clouds drifting between the stars. Nebulae are not distant decorations of the night sky. They are the physical foundation of cosmic structure and the origin of all complex matter in the universe.